Hi, so welcome you all to my lecture on variety. So today we are going to talk about something called affine algebraic sets and affine varieties, and the source book is obviously Harsham. Alright, so let us begin with our discussion. Suppose we have a field K is an algebraically closed field, okay? So what does this mean, algebraically closed field? So algebraically closed field means that K closure equal to K, and that actually implies that whatever polynomial I can take belong from Kx, it must be splitted in linear terms. Means I can split it up like sum over I equals to 1 to n fix, where each fix is of the form ai x plus bi, okay, where both ai and bi belongs to K. So means I can split in such linear terms, okay. Now we define a n K, that is said to be the affine n space, to be as basically K power n, means set of all n tuples. Sorry, is that where n is a fixed, and this is fixed. So then a n K, this is said to be affine n space of dimension n or whatever, is nothing but set of all n tuples where the elements are coming from K. So this particular tuple is said to be point of a n K, and each ai, these are said to be coordinates, okay. So you can easily figure out that if I take n equals to 1, then a1k is nothing but same as K, okay. Now let us consider that we have n belongs to natural number, we have fixed element, and we consider the affine n space a n K is nothing but K power n, okay, affine n space. Now let us consider K of x1 up to xn, means it is a ring of polynomials of n variables where the coefficients are coming from the particular field small k, right? So how can I write these elements of this ring? So basically these are the form f of x1 up to xn, right? Now can we give a characteristic function on this? Means can we express each polynomial as a function, let's say phi f from a power nk to k? For a, can we assign any element like this? So answer is most natural choice should be that if we take any particular coordinate, let's say a1 up to an, then for a particular small f I define phi f like is mapping to f of a1 up to an, okay. So that means it is basically the map obtained by putting value at f, or you can say it is a valuation at f. Valuation at an. Okay, so every small f or can be assigned to such a particular phi f. Okay, so what can you talk about this phi f? You can, so is it a homomorphism? So this is a vector space. In fact, it is a k vector space. This is a k vector space. So is a vector space homomorphism? You can always say that no, it is, because if we take any a1 up to an and plus b1 up to bn, it may not be every time. You should go to f of a1 plus b1 up to an plus bn, but this may not be same as f of a1 up to an plus f of b1 up to bn. Okay, for example, suppose we consider that, let's say n equals 1 and let us take x square plus 1. So then minus n is mapping to 2, 1 is mapping to 2, but where 1 minus 1 is something, but 0 is mapping to 1. So that means this particular condition means f of minus 1 plus f of 1 is nothing but 4. It may not be same as f of 1 minus 1, right? So it may not be a homomorphism always, but one thing can be fixed, that for any particular small f, I can talk about the 0 of small f. Like I can talk about some elements in a power nk which will take 0, I mean which will give value 0 at small k, which is nothing but means I want to say that I can talk about such a set, that is a1 up to an belongs to a power nk such that f of a1 up to an, this is 0, means it is nothing but the 0 set of f. Okay, so I can talk about such a 0 set. By the way, the question is, can you find an identification that satisfies the homomorphism axiom from the above picture? So just consider this particular identification, that is k of x1 up to xn to set of all functions, let's say define functions from ank to k, like every element small f of x1 up to xn is mapping to phi of f. Okay, this is how one can define, and you can see that, I mean, it may not be a homomorphism because this particular one may not be a vector space as well, but this satisfies the homomorphism axiom. You can just have a brief check. Alright, now okay, so I have got anyway that the 0 set of polynomial I have defined, so let us denote it as z of f. So let us consider that, suppose T is subset of k of x1 up to xn. So what about z of t? Z of t is nothing but intersection of all f belongs to t z of f. So it is nothing but set of all a1 up to an belongs to a power n k such that f of a1 up to an is nothing but 0 for all f belongs to t. Okay, so what about now? You see one thing, that z of t is like this, so I can talk about that ideal generated by t. This is an ideal of k of x1 to xn. So what about z of t itself? So z of t is nothing but set of all intersection, means intersection of all f belongs to t, ideal generated by t, it is z of f. Now one thing, note that t is subset of ideal generated by t. That means whenever I take any polynomial from t, and it obviously, any polynomial let's say belongs to t, it obviously get vanished by any element from z of this ideal generated by t. Okay, so that means what? Z of ideal t, this is superset of z of ideal generated by t. Conversely, so one side is very clear, because t is subset of ideal generated by t. In fact, suppose u is subset of v, where both are subset of k of x1 up to xn, then one inclusion is always there, that is z of v should be inside z of u. Okay, this inclusion is always there, because anyway the properties are basically these two inclusions are basically reversing the direction, right? So that's why one inclusion is always there. But in this case, in our case here, the another inclusion will be also fine, because ideal generated by t is nothing but any element, let's say small g, should be written as sum over I equals 1 to, let's say d chi I of x1 up to xn into gamma I of x1 up to xn. So means I can now means each of the chi i's is belongs to t, so this will get vanished by elements from z of t. So of course z of t, g must be get vanished by every element by z of t. So that means z of t, this is also as well as containing z of ideal generated by t. So from both the inclusion actually implies that z of t is same as z of ideal generated by t. Now here is a very beautiful interpretation that I should get, that now note that what is k? K is a field, right? K field means this is Noetherian ring, because it has only two ideals, and Noetherian ring means any FD idea is finally generated, so it is Noetherian ring. So as it's a Noetherian, in fact, when Noetherian ring means what? So any ideal should have any ascending chain of ideals should get vanished. So here also the any ascending chain means there are two ideals only, 0 and the proper ideal, otherwise there is 0 and the exact k, so there are only two finitely many ideals, so of course it should get vanished. So that's why I take k to be a field, so it's Noetherian ring. So as it's a Noetherian ring, then of course I can say that k of x1 up to xn, this is also Noetherian ring. If you remember, there is a very beautiful proper theorem that is playing in between, is nothing but the Hilbert basis theorem. Okay, so that's why I can say that ideal generated by t, this one is finitely generated. So as it is finitely generated, so that means this ideal generated by T is nothing but same as ideal generated by some finitely many element. Let us call it as H1 up to HL. Okay, so that means it is Z of this is nothing but same as Z of this. So means what? It is same as Z of H1 up to HL. Okay, so means if we have any particular, so of always this should belongs to n by T. So that means whenever I can take any T subset of K of x1 up to xn, then Z of T can be considered to be as Z of f1 up to some finite many fs, where each fi belongs to ideal gen phi T. So there is a very beautiful interpretation that it is enough to consider with some finitely many, zero set of some finitely many polynomials, right? Okay. Now, what is Z of T? So first of all, so Z of T subset of A and K, right? So now if we can show that these are the closed sets, okay, then it will be easy for us to define a topology on this particular stuff A power nk, right? And obviously some of you have got convinced that the topology that I want to define via closed sets is nothing but the Zariski topology. So to prove it is Zariski topology, so I need to first show that these ZTs are the closed sets. So suppose we have some finitely many Tn's, then union of I equals 1 to n Z of Ti is nothing but Z of product of Ti's I equals 1 to n. Okay. So as well as if I take any arbitrary collection of T alphas, so then intersection of Z of T alpha is Z of sum over T alphas. So these two are small exercises for you. Hint: use, so just use this one, like how we have proved this one. Use stir and the reasoning. Okay, it is very easy to check. All right, it's a very ground level work, so just try by yourself. So now what about the ANK itself? So ANK is nothing but Z of the zero, Z of singleton 0. And what is phi? Phi is Z of K up to xn. So that means these two are also closed sets. So all these two are closed sets. So I can define a topology, let's say tau z, considering these zt's as the closed set. Okay. Now this is said to be, there is topology on A N, K. Okay. So these ZTs, these are basically said to be as affine algebraic set. So in fact, these are basically algebraic set. Okay. So let us have some workout on how the affine or the algebraic sets should look like. So as an example, that suppose we have n equals 1. So in that case, what is ank? In that case, ank is nothing but a1k, which is the same as k. So basically it's a field, even just a field. So as we have said that, what about z of t? So z of t is nothing but set of all some polynomials f1. I mean there's some finite many polynomials, let's say f1, f2 up to fn. So now f1, fn each are in kx. So each of them can be split up in linear terms. So f1, let's say, contains some product over I equals 1 to let's say m1. So it is nothing but ai minus aix plus bi. Okay. Similarly, each f1 can be written as, similarly f2 can be written as some product of some linear terms such and such fn. Now each are finite, so ultimately I should get that zt is nothing but this product of some finitely many linear polynomials. So that means zt is nothing but finite. So conversely, if we take any finite set, let's say x is subset of kx is finite, then I can write them as like x minus, suppose it is a1 comma a2, then I can write t to be as if x minus a1 comma x minus a2. So like then z of t is same as x. So that's how we can get the algebraic set. So that means whenever n equals to 1, then algebraic sets if and only finite. Now in particular, that is let's say tau z, you say that it is the Jersey topology on A and K is Hausdorff or not. So T2 means I can take any to A1 to AN and B1 up to Bn. This can have some open neighborhood U and V. Sorry. Such that U intersection V is completely empty. So U complement union V complement, this is empty. Now this is closed set, so as these are the algebraic sets are there, so closed sets, so that means it has to be finite. This has to be finite, and this should be itself K, but K may not be. Here is a danger point. K may not be finite. So from this aspect we can say that the Jansky topology that we have defined is not housed off for every K. I mean, in fact, it is not housed off in general. Alright. Now let us have to brush up some concepts related to irreducible topological space. Okay, so suppose what is irreducible topological space? So irreducible topological space means, suppose X is a topological space, then it is said to be irreducible if there does not exist any U comma V. These are closed subsets of X such that U union V it is X. So that means I cannot write these to be as so both should be proper. Means X cannot be written as union of to proper closed subsets, right? Now suppose you have a subset X is a topological space. Then let us say Z is subset of X. Z is irreducible. Means what? Z is irreducible with respect to subspace topology. Now there is a proposition. So what does the proposition say? So let us consider that suppose X is a topological space. So what it means that I cannot write X to be as U union V, where both are proper. Okay. Means what? Is not possible. So this is not possible. So this is not possible means what? This is not possible if and only if X complement equal to U complement intersection V complement. It is not possible for any particular X and U. This should not be possible. So this should not be possible if and only if what? That means U complement intersection V complement equal to phi. So this also should not be complement. So that means X is a topological space is irreducible if and only if this is not possible. This is not possible if and only if this part is not possible means, and this is not possible means for any particular U complement U and V, if let's say any particular two open sets. Let's say it is open set U1, it is open set V1, their intersection should be non-empty. that means x is irreducible if and only if u1 intersection v1 is not equal to c for any two non-empty closed subset u1 and v1. Sorry, non-empty open subset u1 and v1. Okay. So this is okay. Now, so we have got one condition that let us u1 and v1 has non-empty intersection. So let us give this as statement 1. What about the obvious statement from here? So this is possible if and only if, so in fact, what does this mean? In fact, let us consider that U is any open set. So what about U closure? U closure subset of X. So U closure complement intersection U, this should be non-empty. Okay. So U closure complement intersection with U, this should be non-empty. So this is non-empty means U closure, but I mean if it is non-empty intersection, so this is true. So as it has two non-empty intersection, but this is not possible at all. So it is not possible at all because U, in fact, you see that U closure is contains U. So U closure complements in subset U complement. So whenever I take any two any element which is in U and U closure complement, so it has to be in U complement as well. So that is not possible. So that means what? U closure has to be inside exactly X. Okay. So that means U has to be dense. So any okay, so this has to be proper. Any proper open subset of X has to be dense in X. Okay. Similarly, we can show that this actually implies that U has to be connected. Okay, and this will imply basically that U is irreducible with respect to the subspace topology. Okay, so let me give you this to as an exercises. Let me give you this to as an exercises. You just try it by your own, and we'll discuss something called algebraic varieties and Quaternion algebraic varieties in the next lecture onwards. Okay, so just recall and revisit these basic stuffs, and from the next lecture onwards we'll going to head break our in later some advanced topics like projective varieties and algebraic affine varieties and all. in fact, we'll see some exercises that relate to some curves. Maybe we have to give a pause with reading Harshon because maybe we need to go to some geometry algebraic curves through some other books. So we will be discussing all these things tomorrow from next lecture onwards. But I request you to fill up the gaps that I have put as an exercises and make yourself very comfortable with dealing with, let's say, some basic theorems. In fact, we will discuss as well. So first of all is Noetherian ring, Hilbert Dalstanges, okay, and if possible some integral extension. Alright, so just have a brush up with all these basic stuff. We will be discussing in our lecture as per the parapets. Alright, okay, so let's continue. Thank you.